All right, class, this is the Networking 101 lecture, and in this lecture we're going to cover many parts of what you need to know about networking and the internet for this class, and a lot of what we're going to focus on is how denial of service attacks work, how hackers get inside networks, and we'll cover a good portion of the different types of classes of denial of service attacks, from TCP abuse to just raw bandwidth to ICMP, DNS, and next time we'll cover network time protocol amplification, which was used most recently in the world's largest DDoS attack. And should have a disclaimer that this is not a comprehensive coverage of networking. You should really, if you want to really get into networking, take a class. There's several that FSU offers. And we're just going to focus on the networking issues related to the core topics of this class. We're going to cover the data link layer, the link layer, and the IP layer in this lecture, and next time we'll cover TCP layer and application layer protocols and additional topics. The first and foremost thing you should know about the internet: it was primarily designed as a research network, and there were a small number of hosts originally, and perhaps it was designed before many of you were born, depending on how old the people in my class are. And being that, in the original implementation, we've seen issues across the decades that are inherently caused by the trust we placed in different aspects of the network and how it's implemented from its conception. Being a research network, ARPANET was designed such that everyone on the network was trusted. So we trusted that when people say, hey, I am this IP address, that's true. I am this MAC address, that's true. And it grew and grew into a network of networks, and this was supported by IPv4, and then autonomous systems and BGP routing and CIDR subclasses, and eventually when IPv4 nearly was exhausted, NAT, network address translation, came about, and we are still predominantly in IPv4 era, where we are just running on fumes until we have completely exhausted what we can get out of IPv4. And IPv6 is the spiritual successor and designed to provide enough address space to solve all these problems. It also implements things differently, and so some attacks that we see for IPv4 in this lecture, such as ARP, don't apply in IPv6. So the OSI reference model for the internet and how it is implemented, in other words, computer networking, is broken down into 7 layers. At the lowest level is the physical layer, which is the physical medium that the bits are transmitted over, whether it's wires or over Wi-Fi. And then going up is the data link layer, where you have Ethernet frames and Ethernet routing, or rather just communication. At the data link layer, you have essentially IP addressing, and that's where IP routing occurs. The transport is primarily for transmission control and TCP. UDP does not do any transmission control, it just sends it. Doesn't care if you get the message. Then there's session and presentation, which don't really, well, I'll get back to that in a little bit. And then finally the application layer, which is what most users of the internet are familiar with protocols here, such as HTTP. Almost everyone who's touched a computer is familiar with HTTP. So applications and services that provide like web browsing services, mail services, file transfer, this is where those protocols live. And it's designed to be modular in such that I can switch out any form of transport protocol I want, as long and it should be completely interoperable with any other protocols I have going on at the other layers, so that each layer has isolated responsibilities and doesn't interfere with the operations of the other layers. So another model is the TCP/IP model, as a simplified approach, and just breaks it down to 4 layers. And so you see the physical and the data link layer are just grouped into what's called the network access layer. And presentation, session, and application layers from the OSI model are just grouped into that TCP/IP's application layer. So to break down how messages are coordinated from an application layer all the way down, say we have a SVN message update, or if Git is your code versioning repo software of choice, a Git update message. Say it's a bit large, in which case TCP will segment it, and for each segment it will break that packet down and append a destination port and a source port and pass it along to the next layer, which is the IP layer in this case, and it's going to append a destination IP address and a source IP address, and the previous layer segment may also get broken down depending on what the maximum transmission unit for whatever medium is communicating over, and any other limiting factors. Maximum transmission unit, however, is more of a layer 2 restriction. So at the IP layer, the packet is then, when it's done, handed to the layer 2, which is going to be Ethernet here, in which case MAC addressing is handled, so a destination MAC address and a source MAC address is going to be coordinated, and then it's finally communicated over the physical layer. So we're just going to focus on these today. And the physical layer, traditionally, before wireless communications, was seen as having no problems with confidentiality. As long as the attacker wasn't able to physically access that wire you're communicating over, he or she should not be able to listen to your communications. However, with wireless being used, anyone can listen to anything being sent over wireless, and so that technology has raised these confidentiality issues, which various wireless encryption algorithms propose to solve. However, a number of them are horribly weak and easy to crack, such as WEP. And we won't be covering wireless encryption cracking in this class. It's too trivial for me to concern myself teaching. You can go find a tutorial and learn and do it in probably 10 minutes if you want. So before we get past physical layer security, most people don't see the motherboard in your computer or your laptop or your smartphone as a network itself. It is a raw network in that it routes bits over wires from the various interfaces to the processor, to the RAM, to whatever else it may need. And many times, the way these things are configured, there can be vulnerabilities. And many how should I say, industrial control systems, critical infrastructure systems, SCADA systems have essentially serial port networks, in that there's no MAC addressing and it's just raw wires coordinating the communication of various controllers in the field that are controlling physical systems or measuring voltages, measuring pressure, etc., etc. And it's very difficult to figure out what's going on from an outside perspective because you're not able to see things like packets going over the wires. You're having to read raw voltages and perhaps translate them with an oscilloscope. So the purpose of this slide is really to get you thinking outside the box as to what are considered networks. And some of these have interesting configurations, and they provide services to one interface and different services to a different interface. And as we discussed with IPMI, Intelligent Platform Management Interface, and I believe it was homework 1 or 2, I forget, that technology offered many features that many system administrators aren't configuring properly, and their default configurations open up huge gaping security holes for their organizations. So speaking of huge gaping security holes, many devices come with default passwords and backdoors. And you can search for all of these online. It's really easy to find a default password for any given system, whether it's a router or the router your ISP provides you, or an embedded system or SCADA system. For instance, RuggedCom is an industrial network vendor that was bought out by Siemens, and shortly after being acquired by Siemens for a very, very hefty price, it was discovered by security researchers, namely Justin Clark, that the RuggedCom operating system actually has a built-in backdoor, and the username is factory, and it's on by default, and it cannot be disabled, and it's present in all devices running RuggedCom operating system. So, past the physical layer and any initial vulnerabilities or default vulnerabilities in the hardware itself, there are two different kinds of data link layer implementations. There's the wireless network, and then there's the Ethernet network. And that's usually coordinated by switches and hubs. ARP protocol exists here, and this is where ARP cache poisoning attacks to pull off man-in-the-middle attacks occur. And for wireless networks, after the association, there's different types of protocols, but it's effectively the same for most users. It's pretty transparent. So most wireless networks today use the 802.11 standard. There are other implementations, and the 802.11 standard uses ISM radio bands of 2.4 gigahertz and 5 gigahertz, and each of those is divided into channels. There are two types of access points. Effectively, there's infrastructure access points and ad hoc ones, and the features and security features provided by each can differ. So the basic security mechanisms provided, regardless of infrastructure versus ad hoc, should be basic MAC address filtering, the ability to act as a hidden wireless network in other words, tell it to not broadcast the SSID, the ability to toggle whether the device should respond to probe requests, asking who is out there, or network XYZ, are you there? And then there should be some sort of authentication feature, for instance, WPA. This is basically the password to log on to the wireless network itself. That's what this authentication feature is. And the encryption provides the confidentiality aspect of preventing other users from seeing what you're doing, whether they're on the network or not on the network. And the various implementations, WEP, and some implementations of different crypto that are inherently based on TKIP have known vulnerabilities. TKIP is just rather easy to brute force nowadays. AES is still going strong. And in order to do wireless hacking, essentially you have to have equipment that's compatible with it. In other words, you have to have a wireless interface that you can drop into promiscuous mode, so you can listen to packets that aren't addressed to that device or to that laptop. And this also allows you to do discovery, and obviously, since you can listen to other packets, monitoring of what's going on. It also allows you to, not necessarily promiscuous mode, but there is basic functionality of 802.11 to send disassociation or de-auth packets to kick people off networks and do basic aerial denial of service attacks against anyone who can listen to within wireless range. And WEP is rather easy to break. This is effectively the algorithm and about 10 lines of pseudocode to break it. And essentially, one of the main weaknesses is it for the initialization vector or injection vector, I forget what it's called. The IV ranges from bytes 00 to FF, and effectively this is used in the XOR, and XORing something with 00 doesn't do anything. It doesn't perform any transform on the initial data. So that can expose the key depending on the predictability of what the key is encrypting. If it's a known static thing like hello world and you simply XOR it with 00, which is the weak IV, and then you XOR it with the key, well, it's pretty easy to get the key. So the attack time to pull it off really depends on the number of packets you see. If it's a kind of quiet network, it's going to take longer, but on a busy day, say at a coffee shop, you could probably get on the wireless network in under 10 minutes. So this has been used to compromise networks and steal identities from very large retailers and businesses. I'm not sure whether or not the recent Target attack had any wireless hacking component to it, but one of the largest known identity fraud cases in U.S. history was facilitated by weak wireless encryption, and basically the hackers simply just sat in the parking lot outside of the TJ Maxx and got on their wireless network and just started monitoring what's going on, and things that should have been sent in plain text over the network were being sent in plain text, and so they're able to scrape all sorts of credit cards, people's personally identifiable information, and enough to facilitate identity theft and fraud and rip a lot of people off. So going away from wireless to the Ethernet side, there are two main types of devices that coordinate Ethernet networks. There are switches and there are hubs. And a switch, for instance, this is a really slow animation with 2 different frames. For packets that have a specific address, it sends it along just to where the destination IP address should be located, whether it's a neighboring network or a network that can route it to the destination. And it doesn't send it to unintended recipients. However, hubs are effectively multi-port repeaters, and any packet that comes in over a hub is then sent out to every other port on that hub. So if I send it from computer A to computer B, the rest of the devices on the hub will get it, even the printer here at the end. So from a security perspective, a switch offers me much more confidentiality, and an attacker has to have a compromised node somewhere in the middle, say a compromised switch, in order to monitor what I'm sending. However, if I've compromised a single node on a network and it's being supported by a hub, I can view all my neighbors that are plugged into that hub as well as traffic and all their communications. So the next layer, the network layer, we're going to focus on IP, and it's concerned with moving packets between computers. It makes a best effort to do it, and it uses effectively different segments of the IP address to do the routing across different networks, across autonomous systems, and effectively across the world. And it doesn't need the physical address of the destination computer at first, and it leverages a address discovery protocol in order to determine what the MAC address for the destination or the recipient of whatever the traffic is to route it efficiently. So also at the network layer are error message protocols such as ICMP, and it should be noted that a lot of routers actually drop ICMP and packets, and a lot of switches run by service providers just drop ICMP packets outside of ping. So the IPv4 header has essentially various metadata, such as the version of IPv4. IHL is the internet header length. It determines the length of this segment, or I should say packet. As actually the total length determines the total length of the packet. The internet header length determines the length of the header. And then there is a checksum that's calculated for the IP packet, and it's stored here in the header. If you're, for instance, fuzzing a routing implementation at a very, very low level, any packet you generate has to have a correct checksum. That is one of the most basic constraints that is checked prior to processing the rest of the packet. You can fuzz the entire IPv4 packet space. However, if your checksums aren't right, it's going to get dropped at that first constraint. So, however that's calculated, usually some form of CRC. Then the IP header has the source IP address and the destination IP address, and IPv6 has a much greater uh, numerical range to address, and it has a more, I guess you could say, concise header format. It does not have, as you see, many of the metadata, such as time to live, the checksum, fragment, offsets, because a lot of the aspects of it are implemented differently, and I leave the discussion of that for the other networking classes here at FSU, somewhat outside the scope, because we won't be focusing on IPv6 in this class, not this year. So the explanation of the IPv4 header fields are provided on this slide. I am not going to test on them. Perhaps maybe time to live and the checksum may be on some form of homework or test. And as far as the protocols that are specified by the protocol header and the IPv4 header range from ICMP for error handling to specifying what is the protocol being used at the higher layers, such as the transport layers, TCP protocol or UDP protocol, or whether or not OSPF routing is going on. So options, I haven't seen them in use. I didn't write these slides, so I don't know if this is specifically correct. I'm simply reusing Professor Liu's slides. However, each entity on a network, IPv4 network, has at least one IPv4 address. It can have any number at once, and addresses are divided into subnetworks in order to provide routing algorithms, and a router may only have, say, 4 ports, and if it can divvy up the internet into 4 nicely divided subnetworks, effectively the routing table would be all addresses through this range would go to this port, all addresses through this range would go to the second port, and so on and so on. It's effectively what's going on. So there are 2 types, well, there's 3 or more types of addressing. There's you can send it to a specific single destination. You can broadcast a message, or you can broadcast to a subset of recipients on a given network. And regardless of how you address it, the IP layer exists to handle getting the packets to the destination network and recipient. So one of the problems security-wise is that any sender can put whatever IP source address they want and send it out on the wire. Unless your network is very well set up, this is hard to restrict users from doing this. And one of the main attacks, or I guess features this provides an attacker, is that they can send whatever they want to a destination, and the reply to that will be sent to whatever source address he or she provides. And this is used for many denial of service style attacks, especially in the realm of broadcast messages. If you can get every entity on a subnetwork to send a reply packet to whatever source address you provide, you can amplify the damage caused by a single packet that you send to do that, the single broadcast packet. So one method of deterring and preventing address spoofing is doing effectively path verification. And if the hosts that were the hops that were traveled from point A to point B are not the same as whatever you put in the source address to point B, this can be used to determine that there is address spoofing going on, and the router that's doing this can consequentially drop the packets and prevent such style of denial of service attacks. So that's something you should remember for the test. Reverse path verification can be used for combating source address spoofing used in many denial of service style attacks. However, it's not something that can be used on the victim end. It's something that can be used from preventing your networks from being used against someone else in a large-scale denial of service attack. So, address resolution protocol is something you should absolutely know. It is one of the main protocols that is used by attackers to pull off man-in-the-middle style attacks. And effectively, it works like I need the MAC address for 192.168.1.3. I send out an ARP packet saying, who is 192.168.1.3? Tell me, please. Someone, if that IP is being used on the network, will reply, I am 192.168.1.3. My MAC address is xx.yy.zz, etc. And it will send it specifically to your IP address. In which case, the address will be resolved, at least the MAC level address, and the packet will have the MAC address appended in, put into it, and the Ethernet layer will then be able to route it to the destination. So the problem is that ARP is a stateless protocol, and if many ARP implementations cache any response they see, whether or not they are asking for the resolution of any given IP address. Typically, this lets an attacker flood the network with I am google.com's IP address, my MAC address is blah, blah, blah. And this allows them to set up a proxy, effectively a web proxy, and scrape either Google service or hand off whatever traffic you send to Google when you type it in your browser, and sends it to the attacker, and they can spy on whatever you do. However, HTTPS and SSL and IPSec, HTTPS I should rather say, is built on SSL and TLS. But there are ways to prevent this man-in-the-middle style attack. However, ARP will still leave any traffic that's not protected by such mechanisms completely eavesdroppable by the attacker in the man-in-the-middle position. So there are lots of different tools out there for ARP poisoning. I believe this PDF has a decent enough tutorial on how to do it. It's really simple. It's just what I said. You just spam the network with ARP reply messages, regardless of whether or not there was an ARP request in the first place. And the machines are going to cache those responses and use that to perform their packet addressing. So when you type a URL in your browser, if you do not have an IP address for that URL, it goes out and does a DNS request to resolve whatever IP address is for that URL. However, if you have, and then at some point you need to resolve the MAC address, et cetera, et cetera. So if you have an IP address for whatever your intended destination is, and your computer is already caching, say, malicious MAC addresses for that, it's going to automatically just use that destination for its traffic, which obviously can lead to problems. So encryption here certainly helps. IPv6 is moving away from ARP. It doesn't mean you can't do the style attack. It's just implemented differently, and I don't know much about that. The Offensive Network Security course should cover aspects of this, so if you're interested, you can ask the instructor there. Oops. So effectively, this diagram illustrates that if Alice is trying to talk to Bob, and the attacker convinces Alice that he or she is instead Bob, Alice will basically send, I think it's supposed to be an animation, but my PowerPoint viewer has broken it. Alice will effectively send her traffic to the attacker, and the attacker can save and log all the traffic and manipulate it and forward it along to Bob, and this will be a seamless man-in-the-middle style attack handled in such a way. So IPv4 routing effectively relies on routers forwarding packets to where they should go next from one router to the next, and routing is facilitated by forwarding rules that are maintained in each router, and these forwarding rules are maintained by, they're either statically put in there, which is very rare, or they're handled by various routing protocols, which you may or may not have learned about already in other classes. But essentially, the routers autonomously decide where a packet should go, and it tries to ensure that there aren't loops in paths and that paths are optimized. So, for instance, I was talking about IPv4 and CIDR routing, classless interdomain routing, I should have rather said, and using chunks of an IP address to perform basically forwarding and routing. So essentially, forwarding tables have an IP address and some sort of mask of the upper number of bits to match to send to the resulting interface. So 0.0.0.0 indicates the default rule. So any packets coming into this router that don't match the three above forwarding tables will be routed to out to interface 4, which for instance could be out to the internet. And for instance, 128.186.120.2 would route to FSU. And so a packet may match a number of rules in a forwarding table, and at the end of the day, the most specific rule wins, and that one is used to perform the forwarding decision. So, as I said, forwarding tables can be manually set up, which works well in very small networks, or they can be coordinated with OSPF or RIP, and for autonomous systems, this is effectively a group of networks that are on the edge of a network that route the internal traffic of that network around, and as well as to external networks outside of that organization. So the protocols that handle the routing table coordination for inside the organization or inside that autonomous network are protocols such as OSPF or RIP, Routing Information Protocol, for coordinating the router's forwarding tables, but for traffic going to and from the autonomous system to external networks. That's where Border Gateway Protocol and perhaps its alternatives, if it has any, are used. And the internet is effectively split up into autonomous systems, and each autonomous system advertises the networks that it can reach. And this information is aggregated from the neighboring autonomous systems. A autonomous system will communicate with, and collectively, autonomous systems use the information from its neighbors and its neighbors' neighbors to build the gateway forwarding tables. And these can be manually edited, say at the internet service provider level, to dictate how much traffic goes to X, how much traffic goes to Y, how much traffic goes to Z, and etc. And when routes are set up, first and foremost, the most specific advertisement will win and will be used in the forwarding routing decision. And usually, in most cases, the shortest path to a destination will be advertised and will be used. And as I said, this can be adjusted. And sometimes it is adjusted, not by organizations, but by governments in efforts to censor web pages. And there was a case a number of years ago where Pakistan attempted to censor YouTube and did this by manually editing the forwarding tables on the autonomous system routers and switches to basically reroute all traffic going to YouTube instead to a service called Bitbucket. And the problem here was that it also decided to advertise this route to the rest of the world. And its neighboring autonomous systems automatically adopted this path because it was shorter than perhaps the route from the Middle East all the way to the United States to get to the service for YouTube. So the neighboring autonomous systems said, oh, hey, YouTube is instead this way. I can get to it in one hop through Pakistan. And this advertisement was broadcasted to those autonomous systems neighbors, and so on and so on. It spread and spread and spread. And basically, people close to Pakistan ended up, even if they're not in Pakistan, using the bad route. And some people, even far away as even the United States, China, Russia, etc., ended up using the bad route too. So the problem is that BGP wasn't designed back in the day with any security or authentication, and that route advertisement packets were just trusted. And effectively, if the majority of players on the internet that are running autonomous systems worked together to maliciously leverage BGP, it would break the internet, because the internet at the BGP level requires of more people playing good than playing bad in order to work. So BGP is built on top of TCP. You don't normally see BGP updates going over UDP. So any attacks against TCP also apply to BGP, but would really only facilitate a denial of service of BGP updates, which has very limited use that I have trouble imagining scenarios for. So there are ways that the sender of traffic can decide how to route the packet, or can influence how to route the packet. And this is source-based routing. And one of the options in the IPv4 header allows the sender to specify a source route. This was designed back in the day to allow the users of that small research network, the baby days of the internet, to send traffic through perhaps a different university in case the main university on their route was having power issues or their networks were down. And it has stayed in the implementation of IPv4, and it can be used by hackers to avoid security devices. If there are multiple ways into your network and only say 2 of them have a intrusion detection system, the attacker may be able to use source routing to tell it to route through a different node on the network to avoid the security systems. So most routers allow you to drop packets that have source route set, and it is an advisable security choice to go with, to by default drop any packets that are source routing set. So there's not much use of IP options. We're going to skip this slide. ICMP messages, as I said, have been used in the past to do denial of service style attacks to amplify the efforts of a single packet. And many routers and switches, especially at the upper levels, drop ICMP messages, except for ping requests that effectively are just used to facilitate determining connectivity. But ICMP messages usually are for communicating back to the origin of any arbitrary traffic. There has been some problem in routing the given traffic, whether or not the packet is too big for this hop, or the time to live has expired, or the destination is in fact down or unreachable. There are other error messages, such as there are bad fields, and you'll see some denial of service style attacks leveraging IP fragmentation style attacks. I'm not familiar with all of them, so I won't be speaking about it. And I said previously that a host on the network can have multiple IP addresses, and there are 2 models in the RFC that dictate how and when the host should accept packets. The strong model, or strong end system model, this is specified in RFC 1122, and this is going to be on the exam, and I think also on the homework, specifies that if I get a packet from, say on the left is interface 1, on the left is interface 2, if I get a packet from interface 1 on the left, but it's specified the IP address 192.168.17.48, the strong system and end system model dictates that I should drop that packet because it didn't get both the source IP that I have for that interface and that interface correct. However, the weak end system model specifies that if I see a packet that has one of my IP addresses correct, I should accept it, and I must not silently discard it. So the reason I'm bringing this up is that in one of the DEF CON talks in the last 5 years, a researcher started exploring how small office and home routers implemented this, whether they chose the strong end system model or the weak end system model. And he found a actually vast majority of SOHO routers implementing the weak end system model. Now this is a problem because the router's configuration web page that it hosts, you typically type 192.168.1.1 or .0.1 depending on the router in your web browser, and it'll serve up the management web page for that router. Should only be accessible to the local area network and should not be accessible to people out on the internet and people on external networks. However, since most routers at the time implemented chose poorly in their implementation and went with the weekend system model, the researcher discovered that he was able to arbitrarily configure the web pages for a vast amount of small home office routers because it would accept the 192.168.1.1 traffic from the external interface. As a result of that talk, I believe a number of vendors have, the vast majority of vendors have gone about correcting this behavior, and most routers today, I believe, implement the strong end system model and protect against this, this vulnerability. So, as I've been talking about on and off denial of service style attacks, a category of attacks called a Smurf attack is essentially a amplification style attack that relies on sending a very small amount of information that is processed in some way and is expanded to a very large amount of data. So sending ICMP echo requests to a broadcast IP address and spoofing my source address as my intended victim's IP address instead will have all the hosts on that broadcast network reply to my single packet and sending their reply to my intended victim. So this diagram effectively illustrates what's going on in a ICMP echo Smurf attack. There is a website that tracks just ICMP Smurf attacks, and it's powertech.no/Smurf. This is outdated from a year ago. So, moving towards defenses, firewalls do work as long as they're configured properly, and firewalls effectively sit between two networks and are used to protect one network from another. All traffic is supposed to be bottlenecked through the firewall between the two networks in order to facilitate this protection. So there are various different methods a firewall can utilize to protect one network from another. The most primitive one is packet filtering, and effectively relies on rejecting TCP/IP packets from unauthorized hosts or connection attempts from unauthorized hosts. And this can be at the filtering from the IP address layer, or filtering out an entire range of IP addresses, say from a known criminal autonomous system network. Not all internet service providers play nice. Some allow criminals to do whatever they want on their network. And so this is filtering out an entire range of IP addresses as a way to combat that, but nothing stops the criminals from using proxies on good networks. So that's relatively easy to get around. However, filtering out ports is very effective, and it limits the attack surface of a given network, and that's very effective. And speaking of ports, something related to that when IP masquerading is used is network address translation. And NAT is what is effectively keeping IPv4 alive and still running on fuse. And it translates the address of internal hosts as to hide them from the outside world. And there are a number of ways to do it. The most common way of doing it is IP masquerading, and effectively all the hosts on the internal network look like the same IP address to the outside world. In other words, they all masquerade as a given IP. Another protection mechanism is proxy services, and this is more for the application layer, and proxies can break a lot of things. NATs can also break a lot of things that are legitimate, so we'll have a brief discussion of those. VPNs are very commonly used. They're very effective. However, certain technologies such as IPSec, I believe, break VPNs. NATs usually break VPN as well. And there's obviously, you can find firewalls that do fire scanning and content filtering that just search for given strings or signatures in the data portion of a packet. Or filter out, I guess, websites, which is obviously used at a more organizational and business level. So as I said, with packet filters, basically you compare the network and transport protocols to a database of rules, and you forward only the ones that meet the provided criteria, and you drop everything else without necessarily sending an ICMP reply message back to the original sender. So this is usually implemented in all routers. Sometimes it's implemented in the TCP/IP stack of machines, and some of its limitations is that it cannot check all of the headers of traffic. For instance, higher level, the higher layers, such as the transport layer and the application layer, it cannot check the headers there and determine perhaps subtle attacks or deep problems in their headers. That's where stateful packet inspection comes in. We'll talk about that, I believe, next time. So the filters are only sophisticated enough to check the network layer headers, and firewalls, if they have port filtering, that's effectively doing transport layer packet filtering, which is conceptually trivial enough to understand. So network address translation is one of the lesser understood technologies on the internet. It's specified in RFC 1631, and it is designed as a short-term solution for the depletion of the IPv4 range. So classless inter-domain routing, or CIDR, is also another short-term solution. There's an alternative to NAT, and effectively there are 4 ways of doing it. Dynamic translation, or as I said, IP masquerading, is a large number of internal users all appear to external users as a single IP address. And that's coordinated by effectively ports and traffic observation, the firewall or router level. Then there's static translation, which offers no protection or security for the internal users of a network. It simply statically maps one-to-one external addresses to a same size block of internal addresses, making anyone inside the NAT directly addressable and reachable by outside users. Dynamic translation, however, makes it exceptionally difficult for external users to directly touch internal users, if not completely impossible. Load balancing is more of a server-side thing, and a single IP address is distributed across a number of redundant servers. And if one server is getting too much traffic, basically the translation mode will adapt and send spillover or overflow traffic to the other servers so that no server is bogged down too much. So network redundancy translation is similar to load balancing, but it's the reverse. Instead, you have multiple internet service providers or multiple external networks provided to your autonomous system or your network, and depending on the bandwidth going in and out, you adapt and load balance across the different networks you have your traffic. So dynamic translation, or IP masquerading, can be attacked by IP source routing, but almost all routers that I've seen and all firewalls that provide NAT block this by default. So NAT prevents, when in dynamic translation mode, prevents external hosts from making any connection to the internal hosts. And this breaks many protocols that require connecting back to the user, such as IRC. One of the ways around this is UPnP, and a lot of malware and a lot of botnets use UPnP to open up ports to be forwarded to their compromised host, so an attacker can directly talk to them. So the theoretical limit of IP masquerading, because it coordinates all the masquerading over ports. Say you have 80 users all doing web browsing. Well, they're all not going out over port 80. It distributes it across the port range and keeps track of who is what. And then once it gets to the NAT, it translates basically to whatever port the host is using and translates the IP address to the internal address the host is using as well. And then the traffic resumes as normal. So there is a theoretical max of 2 to the 16 connections, but in practice it is usually much, much less. So static translation, as I said, just maps one-to-one an external range of addresses to an internal range of addresses. It provides no protection to the users of the internal network, and any outside attacker can directly address any of the internal users. Load balancing is more concerned with keeping a server, a range of servers up and running and responding quickly and not getting bogged down too much by routing and load balancing traffic evenly across a number of servers. And it only works well for stateless protocols. If your connection suddenly gets handed off from one server to a different server, if you're communicating over a stateful protocol, it's going to completely break. Network redundancy is the reverse of load balancing, but say if Comcast or Time Warner or Bright House goes down, if you have one ISP and it goes down, you no longer can provide your service. You no longer have internet. But if you have agreements with multiple internet service providers, when one goes down, you can fail over to the one that's still up and still provide your service and still make money and still do your business. So NAT in general cannot be used with protocols that require a separate back channel, that do any form of TCP header encryption, and these are some services that NAT usually causes problems with, such as IRC, ICMP also sometimes. IPSec and Internet Key Exchange we'll cover in just a little bit, and encapsulating security payload as well. So for IP masquerading and hacking through it, perhaps one of the most effective and most popular ways to hack through it is to entice the user to visit your website. And this can be done through social engineering, sending them an email saying, hey, click on this, your account's getting shut down, you need to log in to fix it, it's a malicious URL. Or what's being more and more common are watering hole attacks, and that attackers simply just serve up malicious ads on very popular websites, and ads have always had problems serving up malware that directly attack any user that visits the site. And these ads get served up on all sorts of sites. So if you're able to submit a malware ad, you're not going to attack just the users of one site, you're going to attack the users of any sites that have an agreement with that advertisement service. And I believe every advertising service on the internet has, and probably at this very time still does, serve up ads that contain malware. And so it is recommended that all users of any business or organization do ad blocking, because I don't see how it can be done right. Instead of doing that, there are other alternatives that bad guys do, such as just hosting malware on porn and gambling sites and BitTorrent sites. And usually at a business level, these are filtered out at DNS level automatically by IT and the system administration. But the gist of these techniques is that since the victim cannot be directly talked to, we have to entice the victim to visit our malicious web page or visit our malicious service, so we can, after they send the initial connection to us, attack them over that protocol or over that application. So aside from NATs, we've talked about firewalls, now talking about NATs. Proxies are worth mentioning. They can range depending on what layer they're implemented at, such as web application proxies can differ from lower level proxies. And it's effectively a combination of a client and a server, and the internal users send a request to the server portion of this proxy. And this keeps track of which internal users are doing what, and it redirects the data from the request that it passes along to the external networks back to those users that it's keeping track of. And effectively, the address of the address of all the users using the proxy, as from the perspective of the external network, is all the address of the proxy. So this is also a form of IP masquerading. Everyone seems to be the address of the proxy, as was the case in dynamic what's it called, translation with NAT. So this does break some things, and many times the proxy is also part of the firewall, but they can be different nodes on the network. So many networks perform some form of content filtering, such as preventing employees from visiting websites that engage in pornography and gambling online while they're at work. And it can be content filtering at the DNS level, at the IP level, at the packet level, et cetera, et cetera. Virtual private networks, also a very important technology that we mentioned, and it provides an encrypted tunnel from point A to point B across the internet, regardless of where point A and point B are. And this, through encryption, facilitates a private leased wire or leased line going from point A to point B. And once the encrypted tunnel is established, it will stay open and stay secure as long as both hosts aren't exploited. But many organizations allow users to work at home or work remotely, by letting the users connect over VPN. And many firewalls and some routers provide VPN capabilities. Most operating systems do, but the older ones do not. All VPNs should first and foremost have encrypted authentication, where in order to log into the VPN, you send it credentials, username, and password over a already encrypted session, whether or not it's encrypted by SSL, TLS, or whatever. And many VPN clients, the good ones, will prevent you from visiting external networks and the internet while you're connected to the VPN, to prevent a pipe going out of the network straight to the internet over the VPN tunnel, or effectively redirection and exfiltration of data. However, it introduces the risks of stolen laptops, require changing the VPN keys and password, rather the credentials used to perform the encrypted authentication, and also introduces the risk of, if you work at home, if someone really wants to target that network, they may break into your house to go after your laptop. So, at an absolute minimum, a firewall must perform packet filtering, network address translation, and some form of proxying capability. And often it's advisable to just use the firewall machine just for being the firewall. Don't host any services on it. Don't perform any other activities on it. Do not do web browsing on it. It should be a standalone machine that has a very, very small attack surface. So firewalls won't help you when attackers are coming in over the ports that you already allow, such as web traffic, mail traffic, etc. It won't stop malicious emails. So let's see. There are lots of different services you can utilize, and since we're short on time, we're going to cover them all. But we're going to cover we're going to cover at least DMZ, and this is a basic diagram of how a firewall would be implemented in a basic network that has two LANs. One exposes the services of perhaps the organization or the business. So it provides the web server for external users to visit, and also provides the web server for external users out on the internet to visit. Meanwhile, the internal users and perhaps the development network and other sensitive internal services are behind a firewall, and all the traffic between the two and traffic between the internal network going out to the internet is bottlenecked through this firewall. And for DMZ, what would happen is that all traffic, DMZ effectively stands for demilitarized zone, and its DMZ networks are designed for exposing whatever services you want to the world. Effectively, they should restrict any traffic going out, but have few restrictions over the traffic going in, as long as they match the allowed ports. So you may DMZ a range of ports to this subnetwork, and also the internal network is still isolated behind a router. There's also a notion in network architecture as a bastion host, and that is if the bastion host is a singular entity that's exposed to external networks and has no unnecessary services, no unnecessary applications, no unnecessary devices hooked up to it, and just performs the bare functions it's designed to. So whatever is in your DMZ should be effectively considered a bastion host. So the web server should be kept up to date, should only be hosting that web service, and should not be hosting, for instance, any mail service or file transfer service or anything that's completely unnecessary to the purpose of performing website hosting. So there are lots of free firewall software packages. IP tables and IP chains is the most common one. It comes default with most Linux distributions, and we don't have time to cover all these. We're going to cover IPSec, and that'll be the end of today's lecture. IPSec will not be on the exams, so this is all just extra material. But IPSec was a very over-engineered solution to many of the problems that were inherently caused by the trusted perception of the internet in its original design. And IPSec is designed to be transparent to applications, but it attempts to provide authentication at the network layer, and also to provide integrity of IP packets as well as confidentiality of IP packets. So there are two parts of IPSec. There's the Internet Key Exchange, and there's the resulting encapsulating security protocol aspect, and also the authentication header, which is, I believe, optional sometimes. For the first part, there are two phases, and it's very much like an SSL connection, where phase one establishes a symmetric key that will be used to to facilitate basically private communication. And phase two is the resulting connection that occurs over that now encrypted channel. And this is very, very similar to SSL. So phase one establishes a shared symmetric key, provides mutual authentication, and establishes something called the IPSec, the Security Association. It's very expensive and poses a significant performance overhead, and the developers of IKE thought this would be used for all the things and were rather ambitious. So there are various different options for the Security Association. There are various options for authentication, various options for what key format and what form of Diffie-Hellman. Phase two establishes effectively IPSec Security Association, and this is very, very similar to SSL. So once the shared symmetric key is established as a session key, another key can be calculated and agreed upon and then used for resulting communication, or it can perform the rest of the communication over the already established shared symmetric key. So the purpose of all this is to protect the data in an IP packet. So an IP datagram has a header and the data is what's going to be encrypted with IPSec, and optionally with the AH portion of IPSec, the IP header may be encrypted as well. However, as we said, that this can break many things and can be broken by many things, such as IP masquerading, such as any form of actually IP masquerading, whether it's through proxies or NAT and dynamic routing. So, for instance, say we have HTTP traffic and is going over TCP, which is then going over IP. TCP encapsulates the HTTP traffic, maybe breaks it into multiple TCP segments, and perhaps the TCP segments are also broken into multiple IP packets. Effectively, the IP data is going to, in IPSec, I misspoke. The IP data is going to contain the TCP headers, so the transport layer headers, and then eventually the application layer headers are going to be all in this data. And any form of security that relies on inspecting TCP transport layer headers and application layer headers to perhaps filter out attacks would not be able to do this under IPSec because these would be encrypted and the shared symmetric key would not be shared with the firewall or the security device. So the encapsulated security payload and the authentication header mode allow for efficient transportation and adds a minimal amount of extra headers. And in the absence of AH, the original headers can remain depending on what mode of IPSec is. This is, for instance, transport mode. In tunnel mode, this is designed for firewall-to-firewall traffic, and the original IP packet is just completely encapsulated in an IPSec packet, which would be edited to have a new IP header, the ESP AH header, and the original one would not be visible to the attacker, which can provide complete confidentiality even if the attacker has man-in-the-middle capabilities. So this is a comparison. So you have a slide with both of them. However, this will not be tested material. It's just for your own understanding. What was that? All right, great. So these modes have different costs, and so if you're deciding on it, you have to decide whether or not you want to provide just confidentiality or you also want to provide integrity. And what do you want to protect? Do you just care about the data, or do you also care about the IP layer headers and having complete anonymity on the internet at the IP, the network layer? So this is for reference. This is the ESP header format. Won't be talking about it. AH header format. And IPSec is effectively a collection of what I'd consider over-engineered protocols, mechanisms to provide confidentiality, authentication, integrity, and also replay detection at the IP layer, or rather the network layer. And that is it for